All right, so we'll start out here looking at this relationship that if we have the product of two things under the radical, that we can split that. We can take essentially the nth root of A and then multiply it times the nth root of B. Now this comes from that exponential rule that we have that is basically when you have A times B to the nth power is the same thing as A to the n, B to the n. So that's where that comes from, and it's actually just an extension there. So moving these things, separating them like this and moving them in and out of the radicals and things are going to be really the kind of the focus of the manipulation that we have today. Okay, so it also works if we have ratios. We have the similar rule with exponents, and so if we have a number like 20 and we want to simplify it, what we want to do is we want to make sure that all the factors that are square factors can be taken out of the square. And so if we factor 20, 20 of course is 4 times 5 or 2 times 2 times 5. We see the 2 squared. We can break that up into 2 squared times radical square root of 5. And so that simplifies the 2 times the square root of 5. Now if we have another example, we say 125 is the square root of 125. 125 is 5 cubed, so we can take out a 5 squared there. We still have a 5, the square root of 5 remaining, but the simplified expression is 5, the square root of 5. And I guess this is just kind of an extension from that very first one too. If you have the square root of 45, similarly, just start factoring it. And I hope you're feeling comfortable with factoring numbers. You know, basically you can do this successively, like if you look at 45, that's of course 9 times 5, and you factor 9 as 3 times 3, so you have 3 times 3 times 5. So it's really important to always factor these things down to the prime factorization. Because there's many ways to factor a number, but you end up with only one way to factor it with prime numbers. Okay, and that's where you want to get to. Okay, so 84, to me when I look at it, it's even first and foremost. That makes, you know, divided by 2 is 42. 42 is 2 times 21, so I have 2 times 2 times 3 times 7. And of course the 2 squared can come out as just 2, and so we have 2 radical 21. Okay, so why don't you try a couple. Now, I got to different places yesterday with the 4 sections. Some groups did this and some didn't. So so it's the chance that some of you got to this and some of you didn't. So I thought this would probably be a good common spot to start. So why don't we go from here? So try these, and then I'll call on a couple of you to volunteer an answer, not so voluntarily. Yes. Okay, let's look at the first 2 first, and then I'll give you another minute if you need it to complete the other ones. Let's see. I know Justin has the right answer. What's the first one, Justin?
2 root 2.
2 root 2. Okay, so that factors as 2 cubed. You can take out a 2 squared, and you got 2 root 2. Okay. So Brenda, did you get the next one?
The second one?
Mm-hmm.
3 root 2.
3 root 2, because that's 9 times 2, so you can take out the 3 squared. All right. How about the next one here? Brandon, did you get this?
I think it's
3 root 3. Okay, so because 27 is 3 cubed, and so you got power of 2, or you could take a 3 squared out. And then 153, anybody factor that? Kevin, did you get that?
3 root 17.
3 root 17, okay, good. And you know you all know the test to see if something is divisible by 3, right? So obviously when something's even, you just divide it by 2, or the last digit is divisible by 2, and then the whole number is divisible by 2. So with 3, your next candidate, you just add the sum of the digits. So we get 1 plus 5 plus 3 is 9, so that's divisible by 3, and so you know that you have at least a 3 in there, and then that's the beginning of the factoring. It's hard to identify 17 as a factor right off the top. So start with the smallest factors and then wait until you get to some of these larger primes. Okay, so let's do this with variables now. One of the things I mentioned yesterday was that when we take the square root of x squared, that equals the absolute value of x. All right, not just x, because if x equals -3, if we square -3, we get 9, and if we take the square root of 9, we get 3. So that's the absolute value of -3, not -3. So with the even powers on the inside of the radical, we're going to start getting cases where we have to look at what the solution is, what the proper solution is. Now, this is important because we have this issue of the domain. So when we have something like this x squared to the square root, the domain of that is the set of all real numbers, right? You could put in any value, including negative numbers, and get it squared. Now, the range of this thing is that we always get a positive number out of this. And so we have to really be cognizant of the fact that when we actually simplify this, that we only end up with a positive number. And that's the reason why we have to take the absolute value of it, because it simply wouldn't be right if we said negative x. Or not negative x, if we let x be whatever x is, and if x is negative, then that wouldn't be, strictly speaking, true. Okay. So a little bit more on domain and range. So we want to make sure that the range of our original problem and the range of what we simplify it to are exactly the same. Of course, we have to keep the domain the same, and if we see that something changes, then we have to, of course, put in a domain restriction if we lose one of the implicit domain restrictions. But the range, we can usually use the absolute value sign to ensure that we get the right range. Okay, so let's look at the square root of x cubed now. All right, the square root of x cubed is, when we did this with numbers, we were able to factor out, an x squared and end up with like when we had the square root of 27, we had 3 radical 3 was the answer. So let's look at the domain here. If we take the square root of x cubed, that only works when x is greater than or equal to 0. So we have a domain restriction that's implied, actually. And so if we were to do this in the usual fashion, we would get x times the square root of x. Now notice here, when I simplify this x squared, or the square root of x squared, I just get x. I don't have to put the absolute value here, because I already have a domain restriction that says x will never be negative anyway. Right? So if I put an absolute value here, it's pretty meaningless, because x will always be either 0 or more. So I'm going to step through a whole bunch of these, and you'll see, hopefully you'll see the pattern of when you need to use the absolute value and when you don't. Okay, so I already said that when we have the absolute value of x, or if we have the square root of x squared, we get the absolute value of x. And then the second one was, if we take the square root of x cubed, we get x times the square root of x. There's an implied domain restriction that says that x can only be 0 or more, so we don't need to put an absolute value because the absolute value is extraneous.
Why is
It's implied because if you try and stick in a negative here, you can't take the square root of a negative number. Okay, so just the same as you have 1 over x has an implied domain restriction of x can't be 0, right? Because when you plug it in, it doesn't work. Here, when you plug in a negative number, it just doesn't work. So that's what I mean by being implied, that you couldn't, if you wanted to, make this negative, right? Okay, so let's look at the next one now. Here we have x to the 4th, the square root of x to the 4th. So we have 2x squareds that we're taking out, so we ultimately get to x squared. X can be any value, and when we take the square root, is that too small? Am I writing a little small? Because I got a bunch of these, so that's okay. Just here, I'll write this larger on the board to help you keep up here. So if we got x to the 4th, that's going to be the same as this, which is going to be this, right? Because we get an x out of here, and we get an x squared. Why don't I need absolute values with these? It's squared. So you're already going to get a positive. So whatever I stick into the original expression here, if I put in a negative 1, negative 1 to the 4th is going to be 1, and then the square root of 1 is 1. So if I stick in a negative 1 here, I also get just 1. So the signs work out. So there's no absolute value sign needed here. Okay, so the next one in my I-test is the square root of x to the 5th. Okay, so here we have an implied domain restriction, right? You can't have a negative x. And here, when we simplify it, we get the square root of x, no domain restriction needed, right? Okay, the next one is x to the 6th. How about x to the 6th? X to the 6th, how does that simplify? Just ignoring absolute values. X cubed, right? Because we have 3 pairs of 2. But there we have to do the absolute value, because if we stick in a negative 1, let's say here, negative 1 to the 6th power is 1, the square root of 1 is 1, positive 1. But without the absolute value sign, if we just took x cubed, we would get negative 1. So we need to say, oh no, it's positive. So we need the absolute value sign here. Yeah.
I don't understand how for x to the 5th you got x squared, square root of x.
Okay, so x to the 5th is the same thing as x squared, x, right? And so then okay? Now I'm going to have a little faster way to do this a little bit later to show just how you can do this when that exponent is really even large. Like you don't really have to expand it like this when, let's say, we do x to the 11th. Okay, that would be kind of tedious. So I have a different way to do that I'll show you. But anyway, for now, that's what we got. Okay, so if we have x to the 7th now, x to the 7th, the range of this thing is always positive, like all of these, right? Because the square root is always positive. But x to the 7th can be positive or negative depending on what x is. And so we have a built-in domain restriction that says x can't be negative because, there again, if I take negative 1 to the 7th power is going to be negative 1, and we can't take the square root of negative 1 and get a real number. So we're not going to worry about the domain restriction, or we're not going to worry about the absolute value sign, because the only way that this is going to work is if x is 0 or more. So no absolute value sign needed. And then finally, x to the 8th is the square root of x to the 8th is simply x to the 4th, because we have 4 pairs of x squared in there. So that gives us x to the 4th. Any number we put in there, both the square root of x to the 8th and x to the 4th will be positive. So we just write that. So you can see we have a whole variety of answers here. And the only way to get these really right is to think about, number one, is there a built-in domain restriction or an implied domain restriction? And is that reflected in when we simplify it? Or if all real numbers are allowed on the, in the original expression, do we get the proper sign of something when we simplify it? Okay, so there's kind of two ways that you have to look at it. Number one is the, you know, what happens, can you put in a negative number, and do you get out a positive number with the square roots? Now, with more complicated expressions, it's possible if you have a negative sign in front of that, then it always has to be negative, or, you know, all those kinds of things. But that's the reasoning that you have to do. You basically do it mechanically and get the right expression, then ask yourself, where do I need to put the absolute value to make sure that my signs are always propagating through the expression properly? Okay, so let's look at multivariables now. Okay, so let's say we have x times y squared underneath the square root sign. So here the square root of x just stays put, right? There's no simplifying that. But we get the square root of y squared, and of course, just like we got over here with the absolute value, we have the absolute value of y. Now, admittedly, this looks a little funny, right? Absolute value signs in the same expression as a square root is not something you see every day, but nevertheless, this is the literal simplification of this. It is the proper simplification of it in that all the values of y that you can put in, y can be any real number, but we always end up with a positive number, so that's why we have the absolute value. So if I have x squared, y squared, and here we would get out an x and a y, and you don't need to put individual absolute value signs around the variables. This is the same thing. If you wrote the absolute value of x times the absolute value of y equals the absolute value of x and y. When you think about it, this makes it a positive number, then you get a positive number. Here it doesn't, you might end up with a negative number if x and y are different signs, but then you always end up with a positive number. So this is, you know, just a general, in general, simpler to write than distinct absolute values. So you can put it around, you know, the entire expression, if that's the way it comes out. Okay, so now let's take a look at x squared y cubed. Now, how does this work out? The domain of x is all real numbers, right? I can put in any real number. If I put in a negative number, the squared will make it positive, and I can take the square root of that. So x squared will always be positive. Y cubed, if you put in a negative y, or a negative value for y, we'll end up with a negative number. So we have a domain restriction on y, but not on x. And so when we simplify that out, we only need to put the absolute value sign around the x, because the y already has to be positive in order for this square root of y to work. And then now we'll deal with really big exponents. We got x to the 10th, y to the 9th. What does that look like then? What do you think? The square root of x to the 10th is just x to the 5th. X to the 5th, it's possible for that to be negative if x is negative, but it's not possible for x to the 10th to be negative. So we do write the absolute value signs there. And for the same reason that we didn't write the absolute value signs before, this y has an implied domain restriction already, and there's no need to change this because we're starting with a positive or a non-negative number for y to begin with.
Can you explain how you got those numbers?
Yeah. You're having trouble getting the exponents down? Let's hold on to that a little bit, because I am going to address that with larger numbers, and I think that's probably going to be a better time to do that than to take a little, I think it's on the next slide, in fact. Okay? So just bear with me and trust that those are the simplifications. Here we have 120 x squared y cubed, and so this turns out, if you factor the 120, we get 2 cubed, and so we can take out a 2 squared, we could take out that x squared, and we can take out a y squared, And so what we end up with is that when we separate it all out, and then we simplify it out to 2 times the absolute value of x times y times 30y. And we can come back to this particular one if this one's still confusing after we talk about how do we reduce larger exponents. Okay, now before I do this, I guess what I'm going to do is I'm going to go back to this, but let me get to get to Sam's point here. Okay? Did you have another question? Did anybody?
I was just wondering, because only the x was in the absolute value.
Yeah.
On that one.
Okay. Because y is inside this square root sign.
Yeah, the other y, which is y squared.
This y, yeah. Now, if that's all we ended up with, we would have to put the y in an absolute value sign. But this one implies that y is always positive anyway. Okay? Okay, so let me go over, this point here. Let me back up. And okay, so let's generalize first how to remove nth powers from radicals, from factors. Okay, so if I'm going to look at the cube root of x to the 5th, all right, I break that up so I have an x cubed and then an x squared. You see how the x squared and the x cubed make an x to the 5th. And so that cube root of x cubed gives me just an x, and then I'm left over with the cube root of x squared. Okay, so this is for taking out one group of 3 when we have the third root. Okay, so let's say we have x to the 8th. So we can break that up into x cubed times x squared, right? Because 3 plus 3 plus 2 equals 8. And so now we have 2 groups of x cubed, which will give us an x times x, and we'll get x squared out of that. So our solution looks like that. Now what about when we have a really big number? Okay, so let's look at what's happening here. So if I take up here, if I take 8 divided by 3, and I'm just going to do really like 3rd grade long division. This is not, what I mean by that is that we're not going to end up with decimal points, so we're going to use remainders. So if we take, this is going to be 2, and so we take 6, and we end up with 2 remainder 2. Now notice that's what we have. We have 2 groups of 3 that came out as just plain old x's, so we have x squared because we had 2 groups of those 3, and we have 2 x's left over. So there's 2 groups of 3, and we have 2 left over. So these turn out to be x times x, which is just x squared. Now if I have 3 to the 11th, let me use the same thing, where I'm going to take 3 divided by 11 divided by 3, and so that's going to end up to be 3 remainder 2. Okay? So we're just doing real simple division here, integers only. And so my solution is going to be x cubed, which is the number of groups of 3 that I have, and then what's left in the under the radical is what I have remaining, which is those 2. So that's what this division is telling me. The question is, how many groups of 3? Now this 3 here comes from the index of the radical. So I'm saying, how many groups of 3 does 11 have? Well, there are 3 groups of 3 plus 2 left over. So I'm going to take out 3 groups of 3, and I'm going to end up with x cubed, and then the remaining 2 are going to be still in place in the under the radical. Okay, so let me take one that has multiple variables now. And we say, all right, the first, I'm going to look at x, and so I'm going to say 5 divided by 3 is 1 remainder 2. So that means I could take out one group of x cubed, and I'm going to have 2 x's left over. And then for the y's, I'll do the same thing, and that ends up to be 2 remainder 1. So my simplified version is going to be x, because I took out one group of x, and I took out 2 groups of y, and then what I have left over, which is the remainder, is going to be the exponents of what I have left over in the within the radical sign. Okay, is this making sense? We'll have some little bit of practice here, but at least from what's shown, does that make sense? Think so? Okay, so let me go back now that we've talked about that. I know I'm kind of weaving back and forth here. Let's first try this thing with absolute values. So you're going to be able to take out multiple groups of 2 out of here, but the exercise is also a decision: do you need to use absolute values or not, and where do you put the absolute values when you have them? So go ahead and do these, and then we'll talk about that. If x was -3, then we would have -3 squared is 9, so we would have 900. The square root of 900 would be 30, so we want to be sure we come out with a positive number there. What about the second one? All right, Stephen, did you get the second one?
Yeah, x, square root 3, and then, absolute value.
No, I don't think that's right. Anybody else? Yes.
3 squared, x.
Great, like that. So what's the reasoning here?
How I do it?
Yeah.
Okay, well, I kind of broke down the 9, just I square root the 9,
Mm-hmm.
and I had 3 squared and next to the 5th, and then I did the process of having a square, which is the absolute value of 3 the absolute value of square, and then the x to the 5th, which was x squared times the radical.
Mm-hmm. Now, why isn't there a absolute value around there? There's actually 2 reasons why you wouldn't put an absolute value there. Why wouldn't you?
Because the radical implied that it can't have any number.
Exactly. It's implied here that x can't be negative. The other reason is that if this came out, regardless of what was inside the radical, x squared is always positive anyway, right? So you would never have to write the absolute value of x squared, because that's always the same thing as x squared. How about the next one then? Yes?
4y squared square root 3.
Mm-hmm. Ooh, you know, I didn't put a y squared in there. I did up until the last 2, so let me make a correction there. Like that. Okay? Now, look at that order. I got 4 radical 3 times y squared, or you could say, like Sam said, 4y squared radical 3. I'm not too fussy about that. If you were to, read very carefully the fine print in the textbook, it talks about the normal order as being your coefficient and then your variables. And so radical 3 is a coefficient. And so your textbook would probably like this version a little better. But if you came up with this, I would, I'm not going to fuss over that. That's, that's a very simple thing. You generally write from simplest to most complex, and a radical 3, is conveniently at the end of an expression. So I don't think it's a big deal. Maybe others would disagree with me, but to me, it's not a big deal. How about this last one then? The fourth root of x to the sixth power. Okay, Sergio, did you get this?
I got x times the fourth root of x squared.
X times the fourth root of x squared. Ah, but you need an absolute value, right? Because this, x to the sixth is always positive, and then the fourth root is always positive. So when you take out that x is allowed to be negative, but you want the result to be positive, so you put the absolute value around that. Okay? I know these seem a little picky and tricky, right? I mean, they're, yeah.
Wait, how come it's not multiplied again? Because
Well, in this expression, the domain of this is all real numbers, right? I can put a negative number in here. So if I put a negative number in this x squared, I still get a positive value, which I can take the fourth root of. Okay, so that means that it's possible that this x is negative. Well, if it's negative, then my expression is going to be negative if I don't put the absolute value signs around there. All right. So this is this business about how to generalize removing the nth power. Everything that I've showed you before had to do with square roots. Everything on this page has to do with cube roots. And since we already talked about this, I'll kind of march through this a little more quickly, just to kind of remind you that what we're doing is we're breaking these up so we have groups of 3 that we're trying to eliminate, and then simplify that. So here's 2 groups of 3 that we of x cubed, I should say, and so that gives us an x squared on the outside. And then the generalized way to do this is we can count how many groups of 3 or however many groups of anything you have just by using long division. Don't go to the decimal, just use the remainder as the number that are going to remain within the radical sign. So in this case we get x cubed, which the 3 comes from that first 3, and then the remainder 2 is what remains in the radical. So when we have more than one variable, we just treat both variables with the same kind of thing, where we decide, oh, we have 1x, so that's just x to the first times y squared, and we end up with those on the outside. Then what's on the inside is from the remainder, and that's a 2 and a 1. Okay, so hopefully this will be a nice systematic way to do it, where you don't have to, always kind of guess how many groups do you take out, how many groups of those factors, that you can just calculate it now. Okay. So let's talk about simplifying radicals. We've kind of tiptoed around the subject. Yeah, Kevin.
For that x cubed on the second last one, would that be an absolute value though? Just because that could be a negative to x?
No, because the cube root can always be negative, right? So we end up with legitimately a negative number with the cube root. All right? So yet another little detail to kind of trip you up. But yeah, that's really the question is, what happens if x is negative here? Well, x to the 11th is negative, and I can take the cube root of a negative number, so my negatives propagate all the way through. So this will end up being negative as well. So we only have to worry about using the absolute value sign when you have the index of an even number, right? Like if we had the 4th root, we'd have to worry about it, 6th root, and so on. But the 3rd, 5th, 7th roots, we don't have to worry about it, because those can be negative. Okay, so let's talk about simplifying radicals. I've kind of tiptoed around this subject. Let's just boldface lay out 3 conditions that will have to happen before we consider a radical expression simplified. All right, so the first one is all possible nth power factors have been removed. So this is removing all the numbers. So if you have a cube root, you shouldn't expect any exponents higher than a 2. If you have a 5th root, you would expect no exponents within that radical is 4. So in other words, I've taken all the reducible groups out. Now, normally when we simplify something, we want to consolidate all the instances of our variables, right? So if I were to take something really simple, like 2x plus x, we would simplify that into 3x, and we'd only have one instance of x in here. Now here's an example when we do these, where we go from one instance of x to having actually a possibility of two instances. And that's just the way it is, that if we have the cube root of x to the 7th, we have x squared times the cube root of x. Okay, so there's two x's in that expression, and this is considered simplified. Okay, rule number 2 is that no radical contains a fraction. So you know how to deal with these already. We talked about this yesterday. So if you have the square root of 3/4, you separate that out into the square root of 3 divided by the square root of 4, and the square root of 4 simplifies to a 2. So there we have square root of 3 over 2. Or if we have variables like this, we say, okay, split that up into the square root of x to the 7th, and then the square root of y to the 4th is going to be y squared. And so if we now apply the first rule that says that x to the 7th, that 7th is still too high, we can say that's going to be x cubed times x squared over y squared. All right, so you see how that works? So the first two rules we obey. Now, this next one is one that probably is the head scratcher of the group, is that we don't want a denominator of a fraction to contain a radical. Now, you folks are probably still pretty close with your high school friends that are like now seniors, you probably had friends when you were a senior that were juniors and things. So maybe you visit your old high schools and things like that, say hi to your old teachers and everything. Ask your math teacher, why do you have to rationalize the denominator? So in other words, why do we take something that's perfectly good, like 1 over the square root of x, and why do we insist that we multiply that so we get the square root of x over x? And if they're my age or older, they'll probably give you an answer. If they're younger than me, they will just say, well, that's the way it is. Okay? The reason is because computationally, this first one on a calculator is very simple, right? You just take the square root of something and take the reciprocal of it. 2 keystrokes. On a slide rule, which is the way I had to suffer through first couple of years of college, this is nearly impossible on a slide rule. This is drop dead simple on a slide rule. So 1 over the square root of 2 is easier to do on a calculator. Square root of 2 over 2 is easier to do on a slide rule. So that's why they always taught you to rationalize your denominators. Computationally, it's more difficult now. But it's still one of those rules that hang around. And I think if I can editorialize on the way algebra books are written, I think there was one written about 1925 and everybody's copied it since, because they all have the same rules. And rationalizing denominators, you may have perfectly good reasons for rationalizing denominators, and we'll see a couple of those, but as being the ultimate and simplified form, that's questionable. Most people who are numerical analysis will tell you that it really doesn't matter. Okay, so if we have a number like 2/3, there's a lot of things that break our 3 rules with this one. So the first thing is that we have a fraction, so we make the fraction the square root of 2 over the square root of 3, and then we get the square root of 3 out of the bottom by multiplying it by square root of 3 over square root of 3, and then that, of course, gives us square root of 2 times the square root of 3 is square root of 6, and then square root of 3 times square root of 3 is 3, and so we have this rationalized form here. Now, on your handheld calculator, calculating this versus calculating this is about the same, right? I mean, just think about it. You push the 6, push the square root, then push the division sign, push the 3, push equal, and you're there. With the 2/3, you say push 2, divided by 3, take the square root, and you probably don't even have to hit the equal sign. So it's actually fewer keystrokes to do this, and you'll get exactly the same answer. So this is a little bit of an archaic rule. I'm going to ask you, though, to be able to do this, because we'll see that there are some really good reasons why you want to rationalize the numerator or the denominator. for one, it makes adding these terms a lot easier when you do that. Okay. So rationalizing radicals that are square roots, you already see me do this, where you just basically take whatever is the square root here and multiply the expression by 1 in the form of the square root over itself, and so then you get square root of 2 over 2. So if it's a variable, we treat it exactly the same. We get the square root of x over x. Now if we have something like a fraction, we split this up. This is like the last example on the last slide. We split this up into radical 3 over radical 5, and then we take it radical 5 over radical 5, and so we get square root of 15 over 5. And so that's a simplified version of that same thing. Now, one of the things that you want to do first when you're doing this is that you want to simplify the radical, or take out as many factors or as many factors that involve a square before you rationalize it. So if you have something like this, where you have 8 over 3 times the square root of 18, square root of 18 is 3 squared times 2, right? So let's simplify that out first. And so then we have actually 8 over 9 times the square root of 2, and then we rationalize it to be 8 times the square root of 2 over 9 times 2, and of course you can reduce the 8 and the 2 to make that 4 square root of 2 over square root of 9. Or over 9, excuse me, not the square root. Okay? One last one. Here's 4 over x. We get square root of 4 over square root of x. And then so we get 2 over the square root of x. So we've simplified it the best we could without rationalizing it. Last step is to rationalize. And so we get 2 times the square root of x over x. Okay, looks like you're all up with this. So why don't you try a few of these? Okay, so the first one. Okay, everybody follow? How about the second one? Kylene, did you get this? No? Maybe throw it out there.
Okay, I got square root x to the third times y over x cubed, or to the third, or yeah,
The square root of
x
x
to the third.
to the third. Okay, now the first rule was to take out the all the possible factors that are greater than a square, right?
Oh yeah.
All right, so let's split this up first, okay? So we want to take care of that issue first before we rationalize. So we have a square root of x cubed, which turns out to be x times square root of x, and now we rationalize by multiplying it by square root of x over square root of x, and so we get the square root of xy over x squared. All right, a little harder there, but the important thing about this one is to just make sure you're following this path of first taking care of your fractions, dividing them up into separate radicals in the numerator and the denominator. Simplify both of the radicals in the numerator and the denominator, and then rationalize. Okay, so how about this last one then? Anybody get this one? Nicole, did you get this?
I got the square root of 2 over 2y.
Square root of 2 over, yeah, there you go. Okay. Okay, now, we're just about at the end of class, and this one is a little bit more subtle. If we have roots that are greater than 2, how do we rationalize those? So, in other words, if we have the cube root of x, how do we rationalize that? If we just multiplied it by the cube root of x over the cube root of x, we'd end up with the cube root of x over the cube root of x squared, right? That's not what we want. What we want is the cube root of x cubed in the denominator. So what we have to do is multiply it by whatever it takes to get to that x cubed. And so in this case, if we multiply it by the cube root of x squared, then those things turn out to be the cube root of x squared over the cube root of x cubed. And so then that bottom radical then will drop out. And so we have the cube root of x squared over x.
Can you get the cube out of that?
There's no getting a cubed out of it, but this here, when we take the cube root of x cubed, that's just x, right? That's the,
How did you get it from finding the cube root of x squared?
there is no getting over this. I found this because I chose it, because I knew that x times x squared gives me x cubed.
Oh,
Okay, and so that's why that one's in red. You have to choose what that exponent is when you have roots where the index is greater than 2. Okay, so we have to choose that number. A couple more examples and then we'll end class here. Okay, so here we have 4 over the cube root of 9. So if we factor 9, we have 4 over the cube root of 3 squared. Okay, so what are we going to choose to be our rationalizing factor? Well, we want that to be 3 cubed, so we're just going to multiply it by the cube root of 3 over the cube root of 3. So then when we extend that out, we get 4 times the cube root of 3 over the cube root of 3 cubed, which simplifies then into 4 cube root of 3 over 3. And then one last one, multivariable. So we have the cube root of 20x squared over 9y. So let's go through this. So we separate the two, and notice I have a, kind of do the whole thing all in one fell swoop, but notice here when I factor it, I got a 3 squared from the 9, and that's just a y. So in order to come up with a rationalizing factor, I have to rationalize both of those. So the first one I'm just going to use 3, because 3 times 3 squared is going to be 3 cubed. The next one, I'm going to do y squared, because that y squared times y gives me y cubed. And so I have this ending up to be 3y, right? Because my cube root of 3 squared times the cube root of 3 is going to be 3. Cube root of y times the cube root of y squared is that. And I'm just going to take care, multiply everything together up on the top here, and then I inspect it to say, yep, my two exponents are less than 3, and I know my factors of 60 are going to be 2 times 2 times 5 times 3, so that's not going to be able to simplify, and that's where I go. Okay, so there's a couple more examples that are at the end of this, actually in the form of things that show that a little bit more, and then one for you to try, and I think a whole bunch for you to try here. So take a look at those, and I'm going to assign homework on this, and then we'll talk about the homework. It'll be handwritten homework, so we'll talk about it on Friday when you come in. Remember, next Wednesday we're going to have a test on chapters 5, 6, and 7, the sections that we covered.
Do we have a final and that test that we have to
Yes,
take?
yes. You're going to have a test a week now. You're going to have next week, you're going to have this. Week after that, you're going to have your placement. Week after that, the final.